Hello, I am Bob D. Hilster, and I am your particle model guru. Today is part one of talking about static electricity, and in particular the gold leaf electroscope. So this one is today, the gold leaf electroscope. There is also, maybe later, I will cover the pith ball electroscope, the Van de Graaff generator, and the cathode ray tube. Things coming up. I have made two previous videos, one titled The Balloon and Lightning, and the other one is What is Charge in the Particle Model. And then I have a third one listed here if you're interested in a good video other than mine on the electrostatic induction. When using the electroscope, you could watch the one video here at the bottom. So if you haven't seen these and you might want to stop and review them, but then you can come back and we'll continue on. Okay, now the thing that's difficult with the particle model is that it's the attraction and repulsion without a charge. Again, the particle model does not have any physical property that would explain charge. Doesn't matter whether you label it plus or minus, red or green, round or square, nothing of those descriptions would cause it to move. Now, attraction in general, the one thing we have in the particle model that causes attraction is G2 gravity, which can push two objects together when the objects involved cause an imbalance of the G2 force. And this is exactly what you have with G1 gravity when the moon and the earth are pushed together. Repulsion is caused by a magnetic field of the objects interacting and pushing each other away. So repulsion is the more difficult one, but we use the concept of a magnetic field to explain repulsion. Okay, so if you let's talk about G2 force pushing two objects together, and what you have is you have G2 particles flowing this way and this way. There's a lot of loss this way until you get here, causing a net force, F2, to push this magnet to the right, and you get the same thing the other way, pushing the magnet to the left. And the flow of the G1 particle as a magnetic field flows through here and it goes around and does not interfere with the objects being pushed together. They don't cause the objects to be pushed together. They're just a consistent flow in one direction where they don't really hit one another. But when you have magnets repelling each other, you have G1 particles hitting each other. In the case of north to north, you have the G1 particle coming out of the north end of this magnet and out of the north, and they're heading directly towards each other, and you have massive collision here pushing the magnets apart. G2 forces there pushing them together, but in this case the force caused by the magnetic field is stronger than the pushing force, causing the magnets to repel. Have the same thing or a similar thing with the two south magnets, south end, but in this case the G1 particles are not coming at each other, they're going away from each other, entering the south end of the magnet here, entering here. But you do end up with, even though you don't have repulsion here, you do end up with particles hitting here and here. That's the only mechanism that the particle model has to cause repulsion. G2 causes attraction. G1 particles hitting each other in this manner will cause repulsion. So here's a gold leaf electroscope. I got the picture from this link. It has a plate up here and a conductor through all the way down to the bottom, through an insulator, And there's a gold leaf here, a flexible one. In this case, with actually an electroscope with a scale on it, has one of the legs of the electroscope fixed while the gold leaf moves back and forth depending on the charge. And you can sort of gauge how much, but this is not it's not a calibrated scale. You don't know with this instrument anything but the fact that there's some deflection, a little deflection, whether it's momentary or continuous. Gold leaf electroscope. The leaf has to be lightweight because you have to overcome gravity, because you got the vertical force of gravity pushing that gold leaf down. And if it's going to move up, it's going to move up because something pushed it up. And when you use this, what you're going to do is you're going to add or remove G1s from a plastic rod or a glass rod. That's what people normally call charging. In the particle model, we're just adding, for example, plastic rods gain G1s and are designated as negative. In other words, we're going to call it negative even though there is no physical property that makes it negative. I call it negative just to be consistent with current terminology. Glass rods, when you rub it with silk, lose G1s, and they're designated as positive. They're just named that just for a convention. So here's a drawing of a gold leaf electroscope where it's balanced. And the way you obtain a balance is you take a wire and you ground the electroscope, and you ground the rod. What happens is if there is extra G1s or missing G1s, if you have extra G1s on the electroscope, the G1s will flow into the ground until there's a balance, and no more G1s flow either direction. And what that means is that even when they're balanced, there may be incidental motion of G1s because the G2 force is still there, but there's an equal amount in both directions. There's a balance of them. There is either no transfer of G1s, or there's just incidental and they're equal and opposite. Same with this. If you have too many G1s on the rod, it'll drain off into ground. If you don't have enough, G1s will move into the rod. Again, the system becomes balanced, and that's the starting point. And it's a dynamic balance, it's not static. Nothing's really so much static about static electricity, because the G1s exist in the earth, in the electroscope, and in the rod as orbitals around an atom. And orbitals are moving at a very high velocity, and they may appear to be static in the fact that they're contained within the atom, but they're still moving. Okay, so we're going to take a plastic rod and we're going to rub that and add G1s. Plus G1s means I got too many here. So you have a G2 particles coming through here and G2 particles. In a sense, those G2 particles want to push this rod towards this electroscope, or this electroscope to this rod, but the net G1 gravitational force holds the electroscope on the table, and you're holding the rod, not letting it move. So the only thing that can actually move are G1s. Now the net force up here and the net force down here are basically equal, but the thing is that there are more G1s moving down than moving up. Everything in the particle model is never always, it isn't that they only move down or that they only move up, but because there's more here, there's more moving down than there are moving up, giving you a net flow, the red arrow showing a net flow of G1s flowing from the rod to the electroscope. When the G1s flow through this metal, when they flow through the rod, there is no magnetic field here. In order to have a magnetic field, the G1s flowing through here have to spiral in a specific way and to do that. But in this rod, you can. When the G1s flow through a conductor, they move through the conductor in a spiral fashion, setting up a magnetic field. No magnetic field, or maybe small. Now, again, nothing is absolute. There could be a small magnetic field here, but there's distinctly a better, stronger magnetic field in the electroscope. So if we look at the bottom of the electroscope, and this is the fixed leaf, this is the gold leaf which moves, and I'm assuming, as just described, that the G1 particles are moving down in the previous page, which means they're coming at you out of the page. And this point is supposed to be the point of the arrow coming at you. So now if you use the left-hand rule, and here's the left-hand rule, I have it pointing towards me. If you point it towards yourself, you'll see your fingers are curling. Well, this is are moving clockwise. So you got G1 particles around this leaf moving clockwise and around the gold leaf moving clockwise. And as the G1 particle comes to this point and this G1 particle comes to, you have collision where they'll hit each other here or wherever they interact, and it pushes the gold leaf away. This is fixed. G1 gravity is holding this electroscope on the table, but this one gets pushed away. You get magnetic repulsion pushing the gold leaf away. If you use a glass rod, when you charge a glass rod, you are removing G1s, and you get the same thing all over again. You get G1s flowing either direction because of these forces. But there are more G1s in the electroscope than there are in the glass rod, so there's more flowing up than there's flowing down, and hence, again, you have flow of G1s through the electroscope, and it will generate a magnetic field. And in this case, the G1s are flowing into the paper, and when they flow into the paper, you'll see that using the left-hand rule, they're counterclockwise. Either way, when the electrons, the G1s are moving this way, and this G1 is moving this way. When they hit this point, they collide here and here, and in many places in between, causing the gold leaf to move away. So it doesn't matter which direction, as long as the G1 flow through the fixed leg and the movable leg are in the same direction, the magnetic field will cause repulsion and move the gold leaf away. Now you have conduction, induction versus conduction. And induction is the temporary, because the amount of G1s moving is small. It has to overcome the gap and move across the gap. Hence the G2 force is not strong enough to maintain the magnetic field. You can get close enough to establish a magnetic field, but when you remove the rod away from the electroscope, it collapses. But when in conduction, you touch the rod to the electroscope, and when you touch it, you get a much stronger flow of G1 particles through the electroscope, establishing a stronger magnetic field, such that when you take it away, the magnetic field is still there, it's maintained. So in induction, you come up close, the leaf deflects, you go away, it goes back. But when you touch it in the electroscope, the magnetic field is firmly established in the electroscope, and even though you take it away, there's enough of the magnetic field to keep the gold leaf separated. My name is Bobby Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model.